All right, so we're going to solve a second order differential equation. It's nonlinear in y, or rather it doesn't have constant coefficient, so all the usual stuff that we tried before isn't going to work. So we're going to solve this. We're going to do a initial value problem as well, so we'll show you how to add that into the series solutions, and let's just jump in. So we're going to assume that y has a power series centered at 0. So y is the sum from 0 to infinity, c sub n x to the n, and then y prime and y double prime are going to be the usual formulas. So y prime is going to be n, c sub n, x to the n minus 1. Y double prime will be the sum starting at 2 of n times n minus 1, c sub n, x to the n minus 2. And so if we plug all of these in, we can actually do the initial values now or later. I'll show you how that works in either case, but for now I'm just gonna do them later. So let's plug everything in. So let's plug all of these into our differential equation that we have, and it turns out that if we combine all of these, we're going to get that y double prime. So I'm going to need some room here. So the sum starting at 2 of n times n minus 1, c sub n, x to the n minus 2, plus x, which is the sum starting at 1. So the sum n equals 1 to infinity, n c sub n, x to the n minus 1, plus 3 times the sum of y. So that's the sum from n equals 0 to infinity, c sub n, x to the n. That's going to be equal to 0. And what I want to do is I want to take stock here about what's going to happen. What's our smallest power in each case, and so on. So we're going to do the usual thing. We're going to look at what's the smallest term that we got from our first few indices. In here, if n is 0, we get a constant term. Here, if n is equal to 1, we're going to get an x term, because this will be x to the 0, but don't forget the x out front as well. So we'll have an x term there. And on the last sum, we're also going to get a constant term when n is equal to 2. So we're going to have a constant term and a constant term there. And then in the middle, we'll have a linear term, and we'll just have to deal with that. On the right side, I want to just point out this right side is 0. It's just identically 0. But what I'm going to do is I'm going to think of this actually as a power series, because we know that if we have two power series, let's say I've already used c sub n, so let's change that to a sub n. We know that if a sub n, x to the n is equal to the sum of b sub n, x to the n, and they have the same starting index, it doesn't matter what it is, that implies that a sub n is equal to b sub n for all n. Okay, so this is our kind of working assumption for power series methods. We've talked about this. So what I'm going to do is I'm just going to formally think of the right side as a power series. It is 0, but I'm going to think of the right side as the sum of 0 times x to the n, as n goes from 0 to infinity. Right? If I add all those terms up, you get 0 for any x value. So this is the same thing on the right, but now I have a power series. We can do our usual equating the coefficients trick. All we really have left to do is to combine all the terms on the left side of our previous line. So what I'm going to do first, actually, is I'm going to peel off our two constant terms that we're going to have. So remember that we said that we're going to have a constant term here and here, and then we'll have a linear term in the middle. Okay, so we'll have a linear term there. So I'm going to peel off the constant terms from the first and last sum. So from the first sum, if n is equal to 2, we're going to get 2 times 1, c sub 2, x to the 0. And then from there, I'm just going to write, this is the sum, is n equals 3 to infinity, n times n minus 1, c sub n, x to the n minus 2. Plus the middle sum, let's just move the x inside. So that's going to be n, c sub n, x to the n, just x to the n. Again, the sum is going to go from 1 to infinity. And for the last sum, we peeled off the constant term. That's when n is equal to 0. So that's 3, c is 0. And then let's see what else. 3c 0. And we're going to have the sum starting at 1. So from 1 to infinity, c sub n x to the n. And so that's going to be equal to our sum over here on the right. And we're actually in pretty good shape. So we're doing all right. I forgot a plus sign here, by the way. This is 3c naught plus that sum. So we're in pretty good shape. So what I'm going to do is I'm going to just group together the constant terms on the left side. So that's 2c2 plus 3c0. This sum starting at 3, we're going to shift it. And we're going to shift it so that the sum starts at 1. The reason we choose 1 is that that's where the sum starts on the other terms, so we want them to match up. So if this sum starts at 1, that means I'm going to decrease 2 from our starting index, and therefore we're going to increase by 2 our n. So our n's are going to become n plus 2's. So this is n plus 2 times n plus 1, c sub n plus 2, x to the n. And this will be the sum starting at 1, n c sub n x to the n, plus c sub n x to the n. Okay, and something is, no, everything's fine. So on the right side, we're going to have, something looks wrong. Oh, there it is. So this sum should have started at 1, because we peeled off the n equals 0 term. Oh, and I know what else is wrong. We're missing a 3 here. So notice that this 3 here never officially made it inside the sum where it should have. So that should be 3c sub n and 3c sub n. Good. Okay. On the right side, we have just 0. So this is the sum from 0 to infinity of 0 times x to the n. And then we have one final step before we start looking at our recurrence. Our final step is I'm just going to rewrite the left side as a single sum. So this is going to be the sum starting at 1. And what I'm going to do is I'm going to write it as something times x to the n. And so we're going to think about what are the terms that we have in front of our x to the n. So we have n plus 2 times n plus 1, c sub n plus 2, plus the other terms are going to be n c sub n plus 3 c sub n. So plus n c sub n plus 3 c sub n. All of that times x to the n, and on the right side that's going to be equal to 0 x to the n. So it goes from 0 to infinity. So what that means is that each of the coefficients on the left is going to be 0, because we're again comparing these coefficients on the left to 0. So each of those will be 0. And so let's just think what we have now. We have 2c2 plus 3c0 is equal to, actually, I'm sorry, I'm going to go back and do one other thing just to make this one bit clearer. The right side is the sum of 0 x to the n as n goes from 0 to infinity, but just so that it matches up with the left side, let's actually just rewrite that right side. So I'm going to copy this. I'm actually going to do a little iPad magic. I'm going to copy that. And on the right side, what I'm going to do is I'm going to write this as 0 plus the sum from 1 to infinity of 0 times x to the n. I think that really makes it clear that we're setting 2c2 plus 3c0 equal to 0, plus we have these other terms that are going to be equal to that 0. So just so that we can see a little bit more clearly where everything is going and coming from, I'm going to try and separate our terms here. Okay, that got a little squashed together. Okay. So what we're going to do then is we're left with the following equations. We know that 2c2 plus 3c0 is 0. We know that n plus 2 times n plus 1 c sub n plus 2 plus n c sub n plus 3 c sub n, that's equal to 0. And that's equal to 0 for all n starting at our starting index. So for all n greater than or equal to 1. Okay, that's our That's the starting value for the recurrence, so that's going to be the minimum value where this recurrence is true. And so this top equation is going to say, let's let C0 be A. This top equation says that C2 is going to be minus 3A over 2. And again, I don't care about a pattern for now. I'm just going to find the first few terms of the recurrence, and then we'll see about what that means for the for our solution, for the series solution for a differential equation. So our second equation is going to be, my Siri on my phone just turned on, sorry. The second equation is going to tell us that C sub n plus 2 is going to be minus n C sub n minus 3 C sub n over the quantity n plus 2 times n plus 1. And you can even write that a little bit better as C sub n plus 2 is minus C sub n times n plus 3 over n plus 2 times n plus 1. And again, remember that these are all valid for n greater than or equal to 1. So the first n value where this is defined is C3. Okay, so C3 is going to be some value. That means that C1 is actually free to be whatever we want. So I'm just going to write that for now. So C0 is A, C1 is B as usual. We already know C2 is negative 3A over 2. That came from the initial equation that we were talking about. And the other values, the rest of the values, are going to come from the second recurrence. So I'm going to find just a few values here. So C3 is what we're going to get when we plug in n equals 1. So that is going to be minus C1 times, if n is 1, this is going to be 4 over 3 times 2. So that's times 4 over 3 times 2. So that's going to be minus b over, so minus 2b over 3. Okay, because this is 4 over 6, so that's 2/3. And now C4 is going to be minus C2 times 5 over 4 times 3. So that's going to be minus C2. C2 we said was minus 3/2, so altogether that's going to be plus 3/2. A times 5 over 4 times 3. So this is going to be positive 15/2 A over 12. And a better way to write that would be 15A over 24. So that's C4. Let's just do two more. So C5 is going to be minus C3 times 6 over 5 times 4. The 6 over 4 cancels right away to 3/2. So this is minus 3/10 C3. And C3 we said was negative 2/3 B. So that's going to be plus 1/5 B. And then just one more, just for good measure here. We're going to minus C4 times 7 over 6 times 5. So that's going to be minus 7 over 30 times C4. And C4 we said was 15A over 24. So that's going to be, let's think about how this will cancel here. The 15 over 30 will be 1/2. And I guess that's all that cancels. So that's minus 7 over 48A, assuming I didn't make any silly arithmetic mistakes. And now we're ready for our series solution. So we're going to have y as C0 plus C1x plus C2x squared plus C3x cubed, C4x to the 4th, C5x to the 5, plus C6x to the 6th, and so on. And we know all these values. We know that this is A plus BX plus, minus 3/2 A x squared. C3 is minus 2/3, so minus 2/3 B plus 15 over 24A. And I forgot our x to the fourth. I forgot our x cubed term. This is negative 2/3 bx cubed plus 15/4, 15 over 24 a x to the fourth plus 1/5 b x to the fifth, and then minus 7 over 48 a x to the sixth, and so on. So that's going to be our power series solution, and we can do the usual things. We can break this up, and we know that so we know that this is going to be a times, we can just look at our a terms. We're going to have a minus, so this is going to be a times 1 minus 3/2 x squared plus 15 over 24 x to the fourth minus 7 over 48 x to the sixth, and so on, plus b times x minus 2/3 x cubed plus 1/5 x to the fifth, and so on. We don't have any more terms there. So that's our series solution, and if this was not an initial value problem, we would stop there. But it is an initial value problem. All right, so we have our initial values, and we want to figure out exactly how those are going to play a role in our power series. And so there's two things that we can do. One is that we could just figure out exactly what's going to happen when we plug these in. But actually, I want to show you a slightly different way to look at these. I want to look at our power series just to begin with. And this is actually a conversation that we've had, or that you've had rather, with your Calc 2 instructor when you learn Taylor's theorem, when you're talking about these power series, is what exactly are all these coefficients. And so I just want to point out very simply that if you were to take y and plug in 0, what would we get? All the x terms go away, right? So gone, 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 gone. And so we're just left with c0. And so it turns out that our c0 is 4. Y prime of x, if you look at y prime, if you just differentiate this power series term by term, what do we get? We get c1 plus 2c2x plus 3c2 x squared, and so on, 4c4x cubed, blah, 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 blah. Okay, so it turns out that y prime of 0 is c1. And just to do one more of these, just so that we don't think that there's a pattern there that's not there, y double prime is going to be 2c2 plus 6c2x plus 12c4 x squared, and so on. So y double prime of 0 is 2c2. It turns out that if you look at the nth derivative of y at 0, what you're going to get is n factorial c sub n. In other words, these c sub n's are really the value of the nth derivative of y at 0 divided by n factorial. That's why for 0 and 1 factorial, since 0 factorial and 1 factorial are both 1, those are just c0 and 1. So it turns out that our c0, or our a rather, is 4. So I want to add this in here. I'm going to box this off just so that we remember that we have these initial values. Okay. This means that really our solution is going to be, if a is 4, we're going to get 4 times the quantity 1 minus 3/2 x squared plus 15 over 24 x to the fourth minus 7 over 48 x to the sixth, and so on. Right, so if we have 4 being multiplied through, that's what would happen, plus b, which is just 1. In fact, let's not even write it, so it's just plus 1 times x minus 2/3 x cubed plus 1/5 x to the fifth, and so on. And again, a little iPad shuffling here. What we're going to get really is that our solution is going to be y is going to be 4 plus x minus 6x squared minus 2/3 x cubed plus, let's see, 15 over 24 times 4 is going to be 15 over 6. So I guess that could have simplified to begin with, right? 15 over 24 is really, you can factor 3 out of it, so you got 3 over 8. So this is going to be 3/2 x to the 4th plus 1/5 x to the 5th minus 7 over 12 x to the 6th, and so on. And so that's really our solution right there. So if you were to get some sort of a computer algebra system to solve this differential equation, that would be your power series solution. No nice function. It's not going to be anything pretty. Okay, but that's going to be our solution for y. Okay, and that's how these initial values kind of enter the picture in the power series equations. All right.